Oh, here we go. Chapter 5, Introduction to Number Theory. Okay, there's some very interesting concepts in here. All right, so let's go through a little thing here. We'll talk about divisors. So first off, in this number theory, we're talking about integers, okay? So here's a definition. Let n and d be integers, right, where d is not 0. Then we say that d divides n if there exists an integer q satisfying n equals q times d. Okay, so here's some examples. I'm sure you're familiar with the idea that since 21 is 3 times 7 times 3, all 3 and 7 both divide 21. That's fairly straightforward. And this is essentially like it is a theorem for sure. If d divides m and d divides n, then d divides m times n. This is kind of like the, and if d divides m, then d divides mn. This theorem 5.13 is fairly self-explanatory, but go through the proof to make sure you understand what's going on. It's essentially the like a distributive law, Okay, what do we have here? Okay, here's a good definition we need to be very familiar with. So an integer greater than 1, whose only positive divisors are itself and 1, that's a prime number, okay? And you can look at some examples. Okay, here's something kind of interesting. Well, suppose you're trying to check. This is what this theorem says. It says a positive integer n greater than 1 is composite, meaning it's not prime, okay? If and only if n has a divisor d satisfying 2 is less than or equal to d is less than or equal to the square root of n. Well, the reason that's the case is that I imagine when you were younger, you would be given a number and you'd try to find out if it's prime or not, and then eventually you realize that you only had to check up to the square root of n, right? Because if you couldn't find one before that, well, then once you took d times, suppose d was exactly the square root of n, well, d times d, that would be n itself then, I guess, so we'd be done. But if once you went past the square root of n, then you would have found that integer as a divisor by checking something that was less than the square root of n. So you can look at the proof. That's all fairly clear. So here's an interesting little algorithm which appears to be fairly efficient, right? So this algorithm determines whether an integer n greater than 1 is prime, okay? If n is prime, the algorithm returns 0. Okay, so if n is composite, the algorithm returns a divisor d satisfying the condition that it's less than or equal to the square root of n. In other words, a sort of a small divisor. Okay, to test whether d divides n, the algorithm checks whether the remainder, right, when n is divided by d, n mod d is 0. Okay, so let's check it out. N d, so what does it do? Program is prime n. So for d equals 2 to the integer just before the square root of n, if n mod d is 0, then we return d, okay? And that does it. So you check through, and that's how you do it. Now, what's interesting is that this algorithm, although it works and looks very simple, this is not something that happens in polynomial time. You should think about that. But if you think about when you input an integer, you're really not inputting an integer. You're inputting a sequence of integers, okay? Numbers between, say, 0 and 10 or 0 and 1. And the length of that input gets large fast. And so this algorithm is not in polynomial time, even though it terminates in less than square root of n. This particular algorithm terminates in less than square root of n units, but to do that, there's a tremendous amount of calculations that have to occur inside of a traditional computer. So, okay, and that's, I think, what this talks about here. All right, here's interesting. This is very interesting. The fundamental theorem of arithmetic tells us about how integers can be represented. So what the fundamental theorem of arithmetic tells us is that if you're given an integer n, you can actually find a prime factorization of it. There, n is equal to the product of primes, and in fact, these primes are unique. Okay, so that's something you are probably familiar with. And then here's another little theorem: the number of primes is infinite. So there's an infinite collection of primes, and the proof of it's right here, but you can kind of see it's a very elegant proof. Let's see. So what you do is you assume that maybe, I guess what the standard proof is, that you assume that, here, let's just read it, right? Let's check it out. It suffices to show that P is prime. If P is prime, there is a prime number larger than P. Well, that makes sense, right? To this end, let P1 through Pn denote all the distinct primes less than or equal to P. Okay? And let's consider the integer m, which is equal to P1 times P2, blah, blah, etc., plus 1. So you just add 1 to that, right? Now, note that when m is divided by P1, the remainder is 1, right? Yes, that makes sense. Just do it and then you'll see. And the quotient is equal to the P1, P2, all the way down to Pn. Therefore, for all I equal 1 to n, P sub I does not divide m. Okay, so what does that say? So that says that no matter what we choose less than this number m, it doesn't divide m. Well, that's a contradiction, right? Because you see, we have the fundamental theorem of arithmetic, which says that you can divide. You can write a number as a product of primes. So essentially, that's why there's an infinite number of them. Okay. So the very important things that we'll be considering in this chapter and in future chapters. And one is a greatest common divisor, and you've probably maybe have heard of this. Like if you've taken a elementary algebra class, you think about the greatest common divisor, right? And here's the definition: let m and n be integers with not both m and n 0. Okay. A common divisor of m and n is an integer that divides both m and n. The greatest common divisor, written GCD of m and n, is the largest common divisor for m and n. So here's a little example to illustrate this. So the positive divisors of 30 are, and we've just listed them here, right? And the positive divisors of 105 are, and we've listed all those. So if you look through there, what do we find? We find that the common divisors, the ones that are in common to both 30 and 105, are the numbers 1, 3, 5, and 15. Okay? So which is the greatest common divisor? Well, it's 15. It's the largest one. And so that should be somewhat familiar to you as an idea, right? So let's look at this example. It's kind of a interesting one. So if you're doing this by hand, what do you do? Okay, let's see. Let's find the greatest common divisor of 30 and 105 by looking at their prime factorizations. So here's 30 and here's 105. So how do we build it? Well, to build the largest number that divides both of them, you look at the list here. So there's a 3 here and there's a 3 here. There's a 5 here and there's a 5 here. But notice the 2 and the 7, they don't occur in both of the prime factorizations. So what you do is you choose just the 3 and the 5, and that's 3 times 5 is the answer. Well, that leads to this theorem. And if you understand this example, then this theorem becomes fairly obvious, that if you have m and n are integers, where m is greater than 1, n is greater than 1, with the prime factorization, and here they're just listing it. You've got these, you take the primes and you raise them to the power, and that's m and n. Now notice that they've listed, they have the exact same primes listed in both of the decompositions here in the statement. Well, that's because a lot of them are probably have exponents of 0. In other words, we're not saying that they have the same, that there's actually a positive number of primes in common here, but you can really write any number like this, right? Well then, okay, if the p sub I is not a factor, we let a sub I equal 0. I guess that's what I just said. Similarly, if the prime p sub I is not a factor of n, we let b sub I equal 0. So you can just basically write down what the greatest common divisor of m and n is by writing down it's equal to p1 to the minimum of the exponents of a1 times b1, a1 and b1 times p2 to the exponent of the minimum of a2 and b2, etc. And that should be fairly clear that is, if you think about it, that's fairly clear that is the greatest common divisor, okay? And here's an example how that's used, right? This number turns out to be that. This number turns out to be that. So you just look at so here the greatest or the least exponent of 2 is 2. See, and you can see down here what they're doing. There's a 1, 5 to the 0 because 0, right? 7 cubed and 11 to the 0 power, and there you have it, okay? All right, so there's another definition which I think you probably have heard about, and that's the least common multiple. Okay, so if you have if you have two numbers and you can look at the multiples of those numbers, right? And it will look basically, let's look at 30 and 105 again. So the prime factorization. Okay, so let's see what this is. We can find the least common multiple of 30 and 105 by looking at their prime factors. Okay, so here they are, right? Now, what do? We have to write down a number here that has, so that you can actually see. In other words, you can see that the number 30 is a divisor. And so 30 is sitting right here. It's 2 times 3 times 5, right? So that means that 30 divides 210. And here, 105, that's 3 times 5 times 7. So 105 divides 110 also. So there it is, right? And if you remove any of those prime numbers, 2, 3, 5, or 7, you would lose the divisibility of that number by one of either 30 or 105. So that, therefore, we have the least common multiple is this expression that you're looking at right here. This leads to a theorem. So you have the same setup here. You write down two numbers, m and n, using the same prime numbers. And then what you realize is that the least common multiple is that you take the p sub I, but you raise it to the maximum of the a1 and b1, the p2 to the maximum of a2, b2, and et cetera, et cetera. And that should make sense if you stare at that for a while, right? Okay, so here's an example. Here's a number, here's another number. The least common multiple is, well, it's 2 to the maximum of 2 and 4, right? Times 3 to the maximum. And then you can go through that and realize that that's the least common multiple. Okay, and then here's a theorem, which is just kind of if you look at it, it'll make sense. Look at it long enough. If you take the greatest common divisor of m and n times the least common multiple of m and n, you get m times n. Okay? Okay, all right, and there's the proof. Okay, so that's 5.1. Make sure you go through this and you get a familiarity with these two concepts of least common multiple and greatest common divisor. These will become very important in our future studies. So thank you. Bye.